All right. For a recap of lesson 1.6, let's take a look at a change of variable question and a cited limit question. Both of these are from the textbook. The first one is page 105, number 8D. We're asked to evaluate this limit. The limit as x approaches 1 of x to the exponent 1/6 minus 1 divided by x minus 1. With the smallest exponent being not a natural number, it seems like a good time to use change of variable. Let's review the 3 communication steps required to get full marks here. Usually it is best idea to find your power with the smallest exponent and replace that with a new variable with an exponent of 1. Let's, in this case, let u be x to the exponent 1/6. Make that statement. Second part is isolate for any other instance of that variable so that you can replace it. This might have a higher exponent on it later, so you can find an expression for x or for x squared, whatever you need to. Here I'm just going to raise both sides to the exponent 6. To get that x is going to be u to the exponent 6. That's a higher exponent than I'm used to, but at least it's a natural number. And I feel like working with exponents that are natural numbers like 6 is a little bit easier than working with exponents that are rational numbers like 1/6. The last thing we need to do is change our limit. This isn't the greatest example for that because as x approaches 1, up here u approaches 1. You're actually really evaluating another limit here. You're taking the limit as x approaches 1 of x to the exponent 1/6, which will tell you what the limit as x approaches 1 of u is, but we really just sort of think about it as changing behavior. Okay. I encourage you to do this communication inline so that you can just continue your solution from here. So I'm fine with you just having an equal sign sort of coming from down here. So what we're doing is we're writing a different question. Hopefully it's an easier question, and hopefully it has the same answer as the question above. Okay. Now, there's a couple of other reasons why I wanted to take a look at this question. I think someone in class mentioned, could we just use long division to figure out what the quotient would be here? I don't think it's the most appropriate thing to do because you're not actually dividing u to the exponent 6 minus 1 by u minus 1. I can't guarantee that that'll always work either. So I'm going to stick to factoring. And when I have this expression for factoring, I have a couple of choices. I could try factoring it as a difference of sixths. Not a lot of people like doing that, but it is possible, and I'll show you how to factor by a difference of n's in a proof coming up in a future lesson. I guess the two more popular choices then is treating this as a difference of cubes or a difference of squares. Let's see if we can find which approach would be more useful to us. You might think that factoring it as a difference of squares is better because it's an easier type of factoring and it'll use the easiest type of factoring while my numbers are a little bit larger. Someone else might argue that factoring it as a difference of cubes, and I think I'm just going to take a step to write it out explicitly as a difference of cubes. Would be better because you're using the higher exponent level of factoring, which should make our numbers smaller, faster. Let's find it. I'm going to treat it as a difference of cubes first. U minus 1, might as well keep that in brackets. Treating this as a difference of cubes, I'm going to have u squared minus 1 as a factor. And my quotient is going to be, let me just check all the way up to here. U squared times what would be u to the exponent 6? That'd be u to the exponent 4, right? Last term of negative 1 times what gives me negative 1? That would have to be plus 1. And then I've got a minus u to the exponent 4. So since I have 0 u to the exponent 4s, the product of these two terms must be positive 1 u to the exponent 4. If I put in plus 1 u squared, that guarantees that I get. Let's just check with distribution. U to the exponent 6 plus u squared minus u squared plus or minus u to the exponent 4 plus u to the exponent 4 minus 1. Right? In other words, u to the exponent 6 minus 1. I've found that students that try to memorize how to factor by differences of cubes just get it wrong, maybe about like half the time. Check with distribution. There's no need to memorize. So let's see. Now what I have is, I'm not sure if this can factor, and I'm not sure that I care if it can factor or not. because I'm still in an indeterminate form. Should have mentioned that much earlier. That's why I'm factoring. And I'm looking for a factor of u minus 1 in the denominator. Well, I think I see it. Now, see, my choice of do I want to treat it as a difference of cubes or a difference of squares is really just a priority. I think I'm going to have to factor as a difference of squares eventually. Now I've got smaller exponents for a difference of squares. So this seemed to go okay. Let's always show our reader the determinate form before we use our properties in the background, let's say. I think our textbook says use the strategy of direct substitution, but we are not making u equal to 1, so I don't like that wording. Sorry, let me scroll up here. So here's what we're doing. Now we're in a determinate form. We are saying what happens as u gets close to 1. This stays constant at 1. This gets close to 1. That gets close to 2. This gets close to 1. That gets close to 1. This gets close to 1. That gets close to 1. This gets close to 1. So this gets close to 3. So the entire quotient will converge on 1/6. So the value of the limit is 1/6. Okay. Let's back up to here and see how we feel about treating it as a difference of squares first. We want to be flexible in this course. And I think that instead of just asking someone, what should I do here, you want to try both approaches and make your own choice. I don't know that there is one best way of doing things. But let me try visualizing it as a difference of squares. This would be what, u cubed squared minus 1 squared? A lot of students can do this step in their head, by the way, and that's fine if you do. I like showing it for the purposes of our lesson. Let's see. As a difference of squares, I think I'll find an advantage because factoring as a difference of squares seems a little bit easier. Let's be u cubed minus 1 times u cubed plus 1. It's a pattern that I probably have internalized or honestly maybe memorized. A little bit easier than sums or differences of cubes. It's easy to check. U cubed times u cubed is u to the exponent 6 plus 1 u cubed minus 1 u cubed is 0 u cubed minus 1. And then let's make sure that we work with purpose. You might get excited and say, oh, cool, this is a difference of cubes and this is a sum of cubes. That's not cool. Who cares that this is a sum of cubes? Sure, you can factor it, but why? Why would you factor it? What is it that you're trying to do? You're trying to get this out of an indeterminate form into a determinate form. So you're looking for a factor of u plus 1. So that's great that u cubed plus 1 factors, but it does not have a factor of u minus 1 in it. For that reason, I am going to demonstrate that I work with purpose, and I'm not going to factor that. I'm going to factor this difference of cubes. So, I mean, like if I'm avoiding factoring by a difference of cubes because I hope I don't ever have to factor by a difference of cubes, I'm in trouble. The good news is that maybe this difference of cubes is a little bit easier to factor than that difference of cubes. Let's try u minus 1 as a factor. I'm going to be a little tight on space. U times what is u cubed? U squared. Negative 1 times what is negative 1 plus 1? I've got minus 1 u squared. That's got to be plus 1 u squared then. And I've still got a u cubed plus 1. Check with distribution. U cubed plus u squared minus u squared plus u minus 1 is u cubed minus 1. Looks good. Divide those out as long as u isn't 1. Show my reader determinate form. I feel no need to expand. I feel no need to factor. In this format here, even if it's like an unsimplified format, I can easily determine that as u approaches 1. This approaches 1, that approaches 1, that approaches 1, that approaches 1, that approaches 3. This approaches 1, that approaches 1, that approaches 2. The expression approaches 1/6. I think I liked factoring as a difference of squares first. But I don't know, it's kind of a matter of opinion, I think. The better approach was. I'm going to try to squeeze in this other example down here. We'll see if I regret it. The other example I want to look at is a cited limit that actually exists. Usually in class, we only have time to look at a cited limit that doesn't exist. Page 105, number 10D is a decent example. Let's evaluate the limit as x approaches -2 of x plus 2 cubed all over the absolute value of x plus 2. So we have a piecewise function built into here. And this means the definition of x plus absolute value of x plus 2 depends on whether x is greater than or less than -2. And since we're trying to see if the cited behaviors are similar to each other, we're going to have to consider both of those definitions. Fine. So let's see, best way of doing this. I suppose we recognize that it's a piecewise function and we split it up into cited behaviors. We say the limit as x approaches -2 of x plus 2 cubed, x plus 2, whoops, as x approaches -2 from values that are smaller than 2. And we consider the limit as x approaches, or the behavior, sorry, as x approaches -2 from values that are greater than -2 of this expression, 2 cubed, absolute value of x plus 2. Now, so these are two separate expressions that we're evaluating. Off to the side, then, I want to take a look at this definition. I'm going to say that the absolute value of x plus 2 is equal to squiggle, 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 x plus 2 when x plus 2 is positive. The absolute value of a number is the number when the number is positive. That means that I'm working under this condition when x is greater than -2. So what I could do now, if you like, is say, well, under which one of these conditions is the value of x greater than -2? That's when I'm approaching values of x that are approaching 2 from values that are greater than 2, right? Sorry, I got kind of stuck because the question is the answer to the question. When x is greater than -2, that's when x is approaching -2 from values that are greater than -2. So I'm going to replace this piecewise definition with this piece. I'm going to say the limit of this expression in this case is going to be the value of, this behavior for x plus 2 cubed all over positive x plus 2. And then I can finish up this behavior over here and say, look, there's going to be a factor of x plus 2. That's going to leave me with x plus 2 squared. And now I'm in a determinate form. So as x approaches -2, this approaches 0, that approaches 0. That's going to approach 0. That doesn't guarantee that the limit exists. We saw this in class, that sometimes the behavior from the other side was different. The absolute value of a number is the opposite of that number when that number is negative. And that would be under this condition, when x is less than -2. If I'm approaching -2 from values that are smaller than -2, that means that x is less than -2. So I use this definition for the piece. X plus 2 cubed all over the opposite of x plus 2. And then, so these limits usually aren't that exciting. They either don't exist or they're usually equal to 0 or just some sort of finite number in between. You'll see a couple of other examples. I remove factors. I'm left with x plus 2 squared divided by -1. And you can see that if this expression up here were any other number other than 0, the opposite of a number is going to be different than the number. With 0, it doesn't really have an opposite. This approaches 0, that approaches 0. 0 divided by -1 approaches 0. So I don't feel like I need to say that since the behavior from the left is equal to the behavior from the right, then the limit exists. I think I'm just going to conclude the limit as x approaches -2. The behavior from both sides converges to the same number. If I could rewind time here, I think I might actually put in a suggestion that if you wanted to label this expression f of x, then maybe you could save rewriting it here and here and here. You could just say the limit as x approaches 2 of this thing, f of x, is 0. Cool. Behavior from the left equals the behavior from the right. Therefore, here's an example where you have to use cited limits or cited behaviors to discover the limit in this case does exist.